So I want to talk about fairness and transparency in ranking, but to do that, first I need to be clear about what do I mean by fairness in the context of our. So I will start with this definition that they are by Kasper Rasmussen, and they are about, okay, what does it mean to discriminate? And we all understand perhaps that there is like a way of discriminating that is not necessarily wrong, which is simply treating someone different because of a certain property. So if you have ever applied for a job and the job was fairly given to another candidate, well, you have been discriminated in the sense that you have been treated worse than the other candidate. You didn't get the job. But as long as that is based on relevant attributes, then that doesn't need to be necessarily morally objectionable, right? So genetic discrimination is simply, it happens when an agent treats someone worse than another because they have a certain. Now, it's simply a matter of disadvantageous differential treatment, right? You're treated differently and that treatment gives you a disadvantage. Now, wrong happens, which is a type of group discrimination, happens when that property that made you be, that caused that you were treated differently was the property of belonging to a socially salient group. So it was not because you didn't have the correct qualifications for a job that you didn't get the job, but it was because you have a certain characteristic, which is belonging to a socially salient group. And what is a socially salient group? Is a group that is very, very evident that you belong to, like for instance, maybe you're a woman or you're Latino or you whatever, you have some characteristic that is very obvious, you have a certain ethnicity, you speak a minority language, you have an accent, whatever, right? There is a characteristic that places you in a socially salient group, and this characteristic causes a disadvantage for you. This is called group discrimination, right? And this makes, normally group discrimination is motivated either by animosity against people of your group or motivated by the belief that people in your group should not mingle with. Now, statistical discrimination is a form of group discrimination. Statistical discrimination is when this property by which you were discriminated is statistically relevant or based on something that the person believes is statistically relevant. And let me give you the most classical example of statistical discrimination is, suppose that you have a highly qualified woman applying for a job, and she is not given the job because the hiring manager believes that, given that she is a woman, she has a high probability of taking maternity leave. That would be statistical discrimination. It's based on a statistical belief. Now, if on the contrary, this woman doesn't get the job because she says that she will take she intends to take maternity leave, then this is a non-statistical form of discrimination. Maybe it's also wrong, but it's not statistical. It's not based on a statistical belief. It's based on an observation, right? So this is so far we see that there is general discrimination, then inside discrimination there is group discrimination, and inside group discrimination there is statistical discrimination. And in statistical machine learning, an algorithm developed through a statistical learning process can discriminate. We just need to consider two elements. First, that we don't need to necessarily think of intentions or animosity. So many algorithms can be created really with the best intentions in mind and end up being discriminatory. So we don't care about, we don't necessarily assume that an artificial intelligence need to have animosity, but also we don't necessarily assume that the developers have any bad intentions. And we understand that statistically relevant means anything that the machine learning algorithm derives from the training data, which is basically how machine learning algorithms works. Everything they do is deriving these statistical beliefs from the training data, right? So an algorithm can discriminate. In which sense? In the statistical sense. And most often, an algorithm can discriminate in the group discrimination way, which means that it will treat people according to the group that they belong to, not necessarily according to their own characteristics. So let's talk about algorithmic fairness in IR. So historically, the purpose of ranking in information retrieval has been to provide the maximum relevance to the searcher, which This is why most search results are sorted according to decreasing probability of being relevant. Whenever you issue a search in any search system or information access system, issue a search, what you will get are results sorted by decreasing probability of being relevant. So the first result will be what the system believes is the most relevant result for you. Now, in information retrieval, we have always cared about the relevance for the person who is searching. However, we have increasingly started to think about the utility for the people or the objects that are being searched. So traditionally, information retrieval systems were created in the late 70s and in the early 80s, thinking of like a library kind of setup, right? You were searching on a digital collection of books or articles, and you were searching for the most relevant article or the most relevant book for a given query. But in 2021, we search online for a variety of items, and those items are not necessarily documents. You may be searching for a business, you may be searching for information about a political candidate, you may be searching for a person, you may be searching for even for a friend, or you may be searching for a mate, right? And these are all sorts of different searches, and the utility in this case for the objects or the people that are being searched actually matters, right? So if you have a search engine for finding local business, the order in which the business are presented impacts the business success. And if you're learning about a political candidate, the order in which the political candidates are shown or the way in which they are displayed in a search engine actually affect their political success. And you can argue even that a dating app can be also seen as an it's a recommender system, but there is also an element of retrieval. And this retrieval may affect your affective or even your reproductive success. So I would claim that for those who are being searched, there are at least 3 criteria that needs to be fulfilled for those being searched to be treated fairly. First, we need to think that there are certain groups that are protected by law. For instance, people with disabilities or minorities that are protected by law in the sense that they should not be discriminated against. And the first criterion I would claim for those who are being searched is that there should be a sufficient presence of elements of the protected group in a ranking. And this is to prevent some economic type of harm, the distribution of types of harm, right? Also called allocative harm, right? So the lower you are in a ranking, the less probability there is that you will be seen, and that means that your success as a business, as a friend, as a political candidate is affected negatively. Second, there should be a consistent treatment of elements for both groups, right? This means this prevents individual discrimination. Individual discrimination happens when items are not consistently treated, right? What we want in an information retrieval system is that similar items are ranked similarly. Third, there should be a proper representation of protected groups, which prevents representation harm. This has to do this is not so much about the position in which you appear in a ranking, but this is more about how you are portrayed in that ranking, how you are displayed, how you are represented, right? Now, let me give you an example of a representational harm. This comes from a book by Safiya Noble in 2018, where she observed that if you search in Google a query such as Black women or Black girls, you will find highly sexualized results. But that don't happen if you search for white women or if you search for Dutch women, right? It happens for Black women or Black girls. And these representational harms happen when a system reinforces the subordination of a group along certain lines of identity, right? In this case, it is reinforcing a sexualized view of Black women through a certain representation of in a. Something similar happens when you look at search completion or search recommendation, right? They tend to reinforce biases or stereotypes. And here I give you some examples. So, for instance, there are recommendations that are very inappropriate, like for instance, you search for Alexandria Ocasio-Cortez, she's a US politician, and then the search engine recommends to complete this with it doesn't represent properly the fact that this nature of being a politician, right? Or Neil deGrasse Tyson, he's a science communicator, he's black, and the completion is arrested, right? It doesn't necessarily need to be, it's not really correct. And indeed, if you search in Google, in the Google search engine in English, many completions of the type nationality are something don't display anything, right? So if you start searching for whatever, Chinese are something, then Google will offer you very little suggestions, or will offer you suggestions that are heavily editorialized. So they have been constructed by a human. They are not naturally what the search engine would suggest, right? They are editorial suggestions. And there are many types of problematic search suggestions like misinformation, adult content. Now, let's go back to economic harms. And with economic harms, we will usually care about the presence of the protected group, minority group, less privileged group in search results. So suppose we are in a recruitment site. Here, there is this recruitment site called Chink, similar to LinkedIn, and the market leader in German-speaking world. And in the case of Think, we search for several professions, and we found the following, right? If you search for economist, then among the top 10, there is only one woman among the top 10. However, if you search for the top 40, around 30% of them are women, right? So this is interesting, right? At the top 10, there is only one woman. In the top 40, there is more than 10% of women. If you search for market analyst, the top 10 results are 80% are women, but if you look for the top 40%, the results are more balanced. And copywriter is another example where in the top 10 results, 90% are men, but if you look at the top 40 results, then there is a more balanced distribution of men and women. This is an interesting question, whether this is a sufficient presence of women. First, because we observe a couple of things here. The first thing is that in many cases, when there is already like an imbalance, the difference between, for instance, the number of men and the number of women in a collection, this imbalance tends to be exaggerated when you look for the top positions in the ranking, right? So maybe in your collection, there is 30% of there are already women who are economists are the minority, and out of all the economists, only 30% of the profiles are women. But if you look for the top 10 results, this 30% becomes 10%, right? If there is an exaggeration of the imbalance in the top results. So that's the first observation. The second observation is, well, how do this is a ranking, it's not a set. And in a ranking, the order matters. So one could claim, well, it's true that there is only one woman among the top 10 results, but notice that that woman is in position number 1. So it's the most visible position. So it's hard to tell whether being in position number 1, how do you compare this situation with having another rank where you have 2 women, but they appear in position 9 and 10? Like what is best, right? So this is something we'll talk about now. There are many biases that can enter a search system, right? So first, you have biases in the training data that is provided by experts. Many search systems are trained, like especially large-scale search systems, they are trained using, for instance, a learning to rank algorithm that is fed lists of queries and documents that have been editorially selected to represent the best results for a query. And the experts may have their own biases. They may dislike certain results like other results. So there may be privileging, there may be bias for or against certain group. There also can be bias in user-provided training data. And this is more tricky to manage, right? So for instance, what do you do if the users of your system have some biases? Like for instance, in the case of Airbnb, some years ago, it was shown that the amount of rent that a black landlord will charge per square meter was basically lower than the rent that a white landlord could charge for per square meter. And this was not a result of Airbnb. It was a result of Airbnb policy, but it was not intentional on their part, and was to a large extent a phenomenon that emerged out of the behavior of users, right? So the user-provided training data may be skewed, may be biased. And also there can be problems with the document construction, and these are even more difficult to find. So for instance, there is a study comparing the profiles of men and women from Ivy League universities in the United States in LinkedIn. And what they found is that men and women have, in general, they have similar completions of their profiles, but there is a group that is quite different in the sense that men will tend to have many details in their past experience section of the profile, while women will have many details in their skills section of the profile. And this means that any ranking algorithm that is supposed to assign different weights and different importance to different parts of a document will have trouble ranking these two sets of documents equally or fairly, because the documents are constructed differently. So you have different ways in which the documents are constructed. So this is very difficult to anticipate, that your documents will be constructed in a different manner, and then if you try to have a universal ranking function, it will not perform well. It will perform better for some group than for another. Now, there are many ways of measuring how a ranking is fair, right? And there is in 2008, there was a paper about retrievability, and that those ideas remained dormant for 10 years until they were picked up by Thorsten, by Joaquin and Singh, who in 2018, they started talking about exposure, right? In the case of my group, then there is Julius Stoyanovic's group, there have been other developments along a similar thing in 2017, 2019, which is more or less the year in which this all started again to be considered as an important problem. And Singh and Joaquin in 2018, they defined this idea of disparate exposure. So on the right, you see, on the right of your screen, you see the typical result of an tracking exercise. So the parts that you see in red are parts where the gaze, the eyes are fixated the longer. And as you can see, and this is quite natural, top results in a search engine, they tend to attract longer, more attention, a longer fixation of the eyes, more reading, and more clicks, naturally. So each position in a ranking has a certain value, which we will call the probability of being examined, or examination probability, which is how likely a person looking at this page is to look at that result. And that number is different for every result. Particularly, it's quite high for the results number 1, 2, and 3, and it's very low for the other results. And maybe there is a small bump at the end of the page, and there is like a little increase in the last result. But normally, there is some decreased probability of examination. And a ranking will be considered fair if, on average, the exposure that items of one group get is similar to the exposure that the other group gets. This is really difficult to achieve because exposure drops very quickly, while relevance may not drop so quickly. So suppose you have an absolute measure of relevance, which is first difficult to imagine that you have, but suppose you have an absolute measure of relevance of certain profiles to a certain query, right? So you are ranking economists by a certain score that, let's assume for a moment that this score is the true score, right? This is the performance of these economists, or how good these economists are if you want to hire an economist, if you need an economist, right? Now, if you sort the candidates by decreasing score, what you have is that the relevance decreases, like this is the blue bars. The relevance is decreasing very slowly along the list, right? And this usually happens because these scores are very rough approximations, right? Especially if you are in a job search engine, it is very difficult that you have really nailed the exact ordering in which the candidates are by how good those candidates are for the recruiter who is searching for candidates, right? It's very difficult that this is accurate. So there is a lot of noise, and there will be many candidates that will be basically indistinguishable from each other. However, the exposure drops very quickly, and a good rule of thumb is to use a logarithmic discount. This is typically what's used in IR. So in this case, you have that all men have on average a relevance of 0.81 in arbitrary units, and all women have a relevance of 0.78, again in arbitrary units. But the examination probabilities are very different, right? So there is a huge difference in the probability that a woman will be seen in this ranking, and that gap in the exposure that is given to men and women is not proportionate to the difference in the relevance or the estimated relevance of these two groups, right? This is quite problematic, and Singh and Joaquin, they define some ways of re-ranking the items so that you can achieve similar exposure. And there are many variants of the same idea. Another idea is to use a process of randomized merging. So in this case, you assume that you have a list of men and a list of women that have been sorted independently, and you want to merge these two lists in a single list. And for that, you assume that the process is a process of randomized merging, where you will pick with a certain probability an item from one group, and with another probability an item from another group. The more you deviate, from this ideal, from an ideal of a certain probability. Suppose you have 30% of women in your sample. The more you deviate from that 30%, the larger the unfairness that this list has. I'm gonna skip through the details, but basically what you will do in this case will be to measure to what extent that you are observing of candidates that has, for instance, a man, a woman, a woman, a man, a man, a woman, or a candidate that is older than the median, younger, older, younger, and so on, a sequence of groups to which these candidates belong. To what extent is the sequence compatible with the process of randomized merging of two lists? And the group fairness criterion, the rank group fairness criterion, will be the maximum probability that still passes a statistical test that this ranking was actually created by a process of randomized merging. And we have used this criterion to evaluate, for instance, job search engines. Here you have LinkedIn and Viadeo. These are two search engines that operate in Spain, in France, the United Kingdom. There are large differences here in the presence of women across different professions, and these numbers are the maximum P that makes the statistical test succeed, which is roughly equivalent to the presence of women in the ranking, but in an amortized way. We have seen that there are large differences across countries. So there are countries where the presence of women in a certain profession in these collections is larger, but also across platforms there are differences. And more interestingly, there are inconsistencies in the way the masculine form of a profession is used as a generic term, right? I don't know if in Dutch language, maybe somebody can answer in the chat, if in Dutch there is a difference on gender when you speak of a profession, right? So if you're looking for a professor, if you use the same word for a male professor or for a woman professor, or for a cook or for a scientist, my impression is that you may use different words.
Sometimes, yeah, sometimes there are differences, but typically words are indeed just strongly associated towards a gender.
Exactly. Yeah. Thanks. So in this case,
in Greek, it's the same.
In Greek, thank you. In Greek, in French, in Italian, and in German, there are many languages where, and normally your search will be the generic term, and the generic is the masculine term, unfortunately, right? So in this case, what we observed was that there were certain professions for which, if you search for the masculine form, the search engine interprets this as masculine or feminine and shows results from both groups. But there are other professions in the same search engine, in the same platform, for which if you search for the masculine, it means men. And if you search for the feminine, it means women. Right? So there are inconsistencies even in both Spanish and French within the same platform as the way in which a query is expanded. This is called query expansion. You're expanding a one-word query into the disjunction of two words, and this may be or may be not done, and maybe it's done inconsistently, right? So what I'm saying here is that all these algorithmic fairness issues require like a set of testing, like a battery of tests that that perhaps right now doesn't exist and requires you to test the search engine or the system using testing, for example, disaggregated by gender. Now there are other methods for fair ranking. Now, in general, in algorithmic fairness, one defines different moments, different points of intervention for creating a fair ranking. And these points of interventions are, you can either change the training data if you detect a problem in the ranking. You can change the algorithm that creates the model, that means the learner, if you are trying to create a fair ranking, or you can post-process the decision, right, and flip some decisions to make the algorithm pass. These are called pre-processing, in-processing, and post-processing strategies for algorithmic fairness. In most algorithmic fairness subfields, the first strategies that are proposed are post-processing strategies. Post-processing strategies, what they do is that they basically reorder the output of your algorithm in such a way that a certain criterion is fulfilled. They may look at a certain ranking and realize that in this ranking you need to include, for instance, one member from a particular group in a certain position. There are methods both to determine what those quantities should be according, for instance, to a probabilistic ranking test, or even to enforce it, or to enforce it when you have multiple categories. Right? This is all about, and you may even want this in an amortized sense, which will mean that across many queries, an amortized sense means that you may not be able to balance the results for every query, but you may be able to balance the results for every day, so that in a given day, people have issued many queries, and you have, at the end of the day, you have given a sufficient exposure to people of different groups, and you can measure this, but you measure this in an amortized sense, like along the day, not necessarily for every query. And when you detect an unfairness, you can change the ranker so that it gives enough exposure to people in any group. You can also have in-processing methods. In-processing methods for algorithmic fairness typically introduce some sort of penalization. And this penalization is, for instance, given that most of these algorithms try to optimize something, this penalization will be an additional cost of unfairness, right? So you will have an algorithm, for instance, a learning to rank algorithm that is trying to minimize a loss. The loss will be the difference between the output of the ranker for the training set and the training set itself, right? So this is a loss that you try to minimize when you learn a ranking. But you can also include a penalization term for unfairness, right? So that would mean if your ranker is consistently producing results that don't pass a rank group fairness test, or they are not considered fair, then you can change the parameters so that you can pass this criterion. And this can actually this can lead to different accuracy fairness trade-offs, right? So this is a typical tool in algorithmic fairness research, which is to try to determine what is the accuracy that you obtain and what is the imbalance that you obtain. And you cannot get everything for free. So normally, when you want to optimize for fairness, you need to lose a little bit of accuracy, especially if your system is optimal. But normally, you can trade a lot of fairness for a little bit of accuracy, which is what happens here, right? So you can very drastically reduce the discrepancies between different groups and without necessarily having to lose a lot of accuracy, right? And there are, of course, there are very bad points, but you can have different trade-offs of accuracy and fairness in a system. So the other thing you can do is to pre-process the data, right? So pre-process the data would be that you're going to train a learning to run system, and instead of training it with the training data you have, you pre-process your training data to make it fair. And there are some results that can lead to a slightly better system, but this is a very indirect way of controlling for unfairness, right? However, it is a very natural way at the same time. Your training sets should be somehow tested for parity, for balance, for unfair, for fairness. If you don't want to introduce algorithmic discrimination in your system from the beginning, right? So you will have to examine your data, and this is not only a quantitative examination; it also involves some qualitative examination, like where does your data come from, who labeled this data, are these labels, do these labels have many subjective elements, and if so, do different people agree on the type of labels that your data should have? Do they agree on what's relevant and what's irrelevant? And do they have any systematic disagreement on what is relevant and irrelevant? So all these things should be examined on the training data that you feed your system. Remember, garbage in, garbage out, right? So if you feed a system unfair training data, you will have an unfair system, and which is it's quite natural to think of, especially considering that humans, we have our own biases, and there are also structural biases, and most training data that you can take from historical decisions will incorporate certain biases. However, this is not the only source of bias in an algorithmic system. Sometimes the training data may not have evidently biases, but your machine learning method will find one or two features that are very highly correlated with the outcome and somehow exaggerate those features in the model. And some of those features, maybe they are protected features. So this will increase any pre-existing difference that there is in your algorithm system. So let me briefly talk about transparency, right? So transparency is a very tricky issue in algorithmic fairness. And here we have Donald Trump in 2018, and he was saying, well, if you search for Trump news in Google, you will see how biased Google is, because they only show, let's say, progressive media, and they don't show any conservative media. So they are portraying, his claim was that Google was biased against him, right? Or even against conservatives. However, I think what's very interesting about this claim is that it's very difficult to disprove. Like, if you start to think about this, like maybe not a lay person, right, but an expert in artificial intelligence or an expert in information retrieval looks at this problem and say, okay, I want to really provide evidence that this is not true. Or maybe it's true, I want to know if really Google is manipulating the search result. This is a very tricky question, and it cannot be solved without some level of transparency from the search engine. This transparency is very important because search engines and recommender systems today are mostly personalized, which makes things quite delicate. Because, for instance, you attend a large demonstration in your town, you go to a large demonstration with thousands of people, and then you go home and you turn on the TV and you realize that this demonstration is not shown on TV. You can actually claim that that TV station is biased against this demonstration because they are not reporting on something that was so relevant. However, if you don't see them in your Facebook feed or your Instagram or your whatever, whenever you get the news from, you will never know if you are not seeing these results because they were selected by the algorithm, they were not selected by the ranking algorithm for you, or whether this was really manipulated, right? So it's very difficult to claim or to even to prove that things are being manipulated or not. So this transparency is really problematic when you have a system. And there are some methods to achieve transparency in rankings, such as including nutritional labels. And there are some proposals to include, like with algorithms like nutritional labels, or like include even a proposal of an algorithmic prospect. This is from Emma Galdon and other people. They speak of the idea of an algorithmic prospect as a description of how an algorithm was constructed, so that you can so that you have at least have some transparency about these algorithms, right? Either by nutritional labels or by a prospect or something that explains how an algorithm works. And if you think about it, think that, for instance, the nutritional labels in food are, now we take them for granted, but it's quite technical information, right? I don't know how much magnesium my body needs, like every week, or how I don't know these numbers, and probably and many others, right? But however, we have like a standardized ways of labeling food, so that I know that you can tell if you are taking enough of this or enough of that nutrient, right? And so I think something similar can happen with algorithms and with. Now, let me conclude so that we can take some questions, like by saying that algorithmic fairness started mostly in machine learning and data mining, and it's a little bit less studies in information retrieval and recommender systems. Sometimes it involves a very exciting algorithmic puzzle, sometimes it doesn't, and it's a matter of like trying to understand. Algorithmic fairness is a very interdisciplinary research discipline where you need lawyers, you need scientists, you need moral philosophers, you need more people looking at these problems, because they are not defined like only technically, right? There is no middleware for fairness that you can plug into any architecture and will make the system fair. That's realistic, right? And we need to understand, okay, whenever you have a problem, like what are you trying to solve, right? Sometimes you want to remove discrimination, sometimes you want to provide equal opportunity. These things are not the same. Sometimes you want to make sure that that a minority group is represented, even if that detracts from the accuracy of the utility of your system. And in other times, your system is both inaccurate and discriminatory, and you want to remove discrimination because of that. In the slides that I have shared with you, there are also links to to a recent survey by Meike Selite. She's a PhD student of mine, and she had this survey published in March 2021. There is a great tutorial by Michael Ekstrand and collaborators on fair information access. And in 2022, there will be a conference in Korea on fairness, accountability, and transparency. With that, I will take your questions.